The range is the difference between the cooling tower water inlet and outlet temperature. The formula for cooling tower range in degrees Celsius is cooling water inlet temperature minus cooling tower water outlet temperature. A high cooling tower range means that the cooling tower has been able to reduce the water temperature effectively and thus performing well. Approach is the difference between the cooling tower outlet cold water temperature and ambient wet bulb temperature. The formula for approach is CD approach in degrees Celsius is cold water outlet temperature minus the wet bulb temperature. The lower the approach, the better the cooling tower performance. Also, the approach is a better indicator of a cooling tower performance. Effectiveness is the ratio between the range and the ideal range. The formula for cooling tower effectiveness is cooling tower effectiveness in terms of percent equals 100 times cooling tower temperature minus cooling tower outlet temperature over cooling tower temperature minus wet bulb temperature. The higher this ratio, the higher the cooling tower effectiveness. Cooling capacity is the heat rejected in kilocal per hour or tons of refrigeration given as product of mass flow rate of water, specific heat and temperature difference. Evaporation loss is the water quantity evaporated for cooling duty. Theoretically, the evaporation quantity works out to 1.8 cubic meter for every 1 million kilocalories heated rejected. The following formula can be used. Evaporation loss equals 0.00085 times 1.8 times circulation rate times temperature 1 minus temperature 2. Temperature 1 minus temperature 2 is the temperature difference between inlet and outlet water. Cycles of concentration, or the COC, is the ratio of dissolved solids in circulating water to the dissolved solids in makeup water. Blowdown losses depend upon cycles of concentration and the evaporation losses. And lastly, liquid-gas ratio is the ratio between the water and the air mass flow rates. The formula that can be used are the following. L times T1 minus T2 equals G times H2 minus H1, or L over G equals H2 minus H1 over T1 minus T2.
The goal of the following discussion is to know the factors which can be manipulated to improve the energy efficiency of a cooling tower. The main areas for improving the energy efficiency of cooling towers are selection of the right cooling tower, fields, pumps and water distribution system, and fans and motors. First, we will consider the selection of a cooling tower. Once a cooling tower is in place, it is very difficult to significantly improve its energy performance. A number of factors are of influence on the cooling tower's performance and should be considered when choosing a cooling tower. Capacity, range, approach, heat load, wet bulb temperature, and the relationship between these factors. We will start with capacity. Capacity in terms of heat dissipation and circulated flow rate are indication of the capacity of cooling towers. However, these design parameters are not sufficient to understand the cooling tower performance. Therefore, other design parameters are also needed. Cooling towers are usually specified to cool a certain flow rate from one temperature to another temperature at a certain wet bulb temperature. When the size of the tower has to be chosen, then the approach is most important, closely followed by the flow rate, and the range and the wet bulb would be of lesser importance. Let's take a look at the range. The range is difference between the cooling tower water inlet and outlet temperature. The range is thus determined not by the cooling tower but by the process it is serving. The approach is also important. This is the cold water temperature minus the wet bulb temperature. As a general rule, the closer the approach to the wet bulb, the more expensive the cooling tower due to increased size. Usually a 2.8 degrees Celsius approach to the design wet bulb is the coldest water temperature that cooling tower manufacturers will guarantee. Next, we'll consider the heat load. The heat load imposed on a cooling tower is determined by the process being served. Process heat loads may vary considerably depending upon the process involved and are therefore difficult to determine accurately. On the other hand, air conditioning and refrigeration heat loads can be determined with greater accuracy. The degree of cooling required is controlled by the desired operating temperature of the process. In most cases, a low operating temperature is desirable to increase process efficiency or to improve the quality or quantity of the product. However, in some applications, for example in internal combustion engines, high operating temperatures are desirable. The size and cost of the cooling tower increases with increasing heat load. Purchasing undersized equipment if the calculated heat load is too low and oversized equipment if the calculated heat load is too high is something to be aware of. In the selection of cooling tower, we must also consider the wet bulb temperature. Wet bulb temperature is an important factor in performance of evaporative water cooling equipment because it is the lowest temperature to which water can be cooled. For this reason, the wet bulb temperature of the air entering the cooling tower determines the minimum operating temperature level throughout the plant, process, or system. The following should be considered when selecting a cooling tower based on the wet bulb temperature. Theoretically, a cooling tower will cool water to the entering wet bulb temperature. In practice, however, water is cooled to a temperature higher than the wet bulb temperature because heat needs to be rejected from the cooling tower. A pre-selection of towers based on the designed wet bulb temperature must consider conditions at the tower site. The designed wet bulb temperature also should not be exceeded for more than 5% of the time. In general, the design temperature selected is close to the average maximum wet bulb temperature in summer. Confirm whether the wet bulb temperature is specified as ambient or the temperature in the cooling tower area, or inlet, the temperature of the air entering the tower, which is often affected by discharge vapors recirculated into the tower. As the impact of recirculation cannot be known in advance, the ambient wet bulb temperature is preferred. Confirm with the supplier if the cooling tower is able to deal with the effects of increased wet bulb temperatures. The cold water temperature must be low enough to exchange heat or to condense vapors at the optimum temperature level. The quantity and temperature of heat exchanged can be considered when choosing the right size cooling tower and heat exchangers at the lower cost. The relationship between range flow and heat load. The range increases when the quantity of circulated water and heat load increase. This means that increasing the range as a result of added heat load requires a larger tower. There are two possible causes for the increased range. The inlet water temperature is increased, and the cold water temperature at the exit remains the same. In this case, it is economical to invest in removing the additional heat. The exit water temperature is decreased, and the hot water temperature at the inlet remains the same. In this case, the tower size would have to be increased considerably because the approach is also reduced, and this is not always economical. Relationship between the approach and wet bulb temperature. The design wet bulb temperature is determined by the geographical location. For a certain approach value and at a constant range and flow range, the higher the wet bulb temperature, the smaller the tower required. For example, the approach stays the same at 4.45 degrees Celsius and the wet bulb temperature at 26.67 degrees Celsius. The heat picked up will be 15.5 kilocalories per kilogram air. This means that there will be a smaller tower needed compared to a lower wet bulb temperature, 21.11 degrees Celsius, which has less heat picked up, 12.1 kilocalories per kilogram air. Lower wet bulb temperature corresponds to larger tower needed. The reason is that air at the higher wet bulb temperature is capable of picking up more heat. We have already tackled the selection of cooling tower. Next, we will discuss the selection of fill media. In a cooling tower, hot water is distributed above fill media and is cooled down through evaporation as it flows down the tower and gets in contact with air. The fill media impacts energy consumption in two ways. Electricity is used for pumping above the fill and for fans that create the air draft. An efficiently designed fill media with appropriate water distribution, drift eliminator, fan, gearbox, and motor would therefore lead to lower electricity consumption. Heat exchange between air and water is influenced by surface area of heat exchange, duration of heat exchange, and turbulence in water, affecting thoroughness of intermixing. The fill media determines all of this and therefore influences the heat exchange. The greater the heat exchange, the more effective the cooling tower becomes. From the table, we can see that there are three types of fills. Splash fill media, or the splashing water over the fill media into smaller water droplets. Film fill media, in which water forms a thin film on either side of fill sheets. Low clogged film fills, on which higher flute sizes were recently developed to handle high turbid waters. Example, seawater. From the table, we can see the different parameters for the different fill media. The liquid to gas ratio, heat exchange, pumping costs, which all impact on energy use. The table compares these parameters between the three fill types. From the table, we can see that film fill media is more efficient than the two.